Hello, my name is Wilson Farrell, and today I'd like to make a presentations about a certain mathematical topics. And these mathematical topics will be about the Cauchy sequence. Alright then, let's start this presentations with some introductions. In these presentations, I'll be start with some explanations about the Cauchy sequence, while also giving an explanation on the Cauchy filters and the Cauchy nets. We'll be following up with the definitions and the proof. We'll also finish these presentations with the problems and the solutions. Alright, let's get started. Cauchy sequence is known to be a sequence where the elements becomes closer to each other as the sequence progresses. And no matter how far the sequence has goes, both sequences will never get close to each other. The Cauchy sequence is named after the famous mathematician named the Augustine Louis Cauchy. The Cauchy sequence are known to be useful for majority of the mathematicians due to, unlike the definitions of the convergence, where it considers both the terms and the limit values. The criterion for convergence in a complete metric space are depending on the term of the sequence itself. The Cauchy filters and the Cauchy nets generalize the Cauchy sequence in the more abstract uniform spaces. The Cauchy filter is a filter that contains the small sets of the uniform space. And every convergent filter or or any filter that is considered to be finer than the Cauchy filter itself are counted as a Cauchy filter. Uniform space where the every converged Cauchy filter is in is known as the complete space. The Cauchy net is a function where the domain counts as the directed sets and some topological space are usually its codomain. The Cauchy net is also known by another name, which is the Moore-Smith sequence. The Cauchy net generalizes sequence in a metric space and primarily used in analysis and topology field. The Cauchy nets are also corresponding with the Cauchy filter. Here are the definitions for the Cauchy sequence. The definition states that we let the AN to be the real number sequence, where AN is said to be the Cauchy sequence if for all epsilons greater than 0. There exists n0 in n such that the AM minus AN is lesser than epsilons for all Mn is greater equals to n0. And below here are the example of the graph of the Cauchy sequence. As you can see, here are the AM and the AN, and and here are the progress their progresses. And as you can see, as the progress goes, they slowly get closer and closer to each other. But no matter how far their progress are, they will never end up close to each other. They sure get closer, but they will never get close. The definition of both can be simplified as the sequence is said to be Cauchy sequence if for each epsilon greater than 0, there exists a positive integer and in n such that the an plus b minus an is lesser than epsilon for all p greater than 0. The remark states that the Cauchy sequence can be considered as a sequence with its term and with each element slowly getting closer to each other as it progresses. The notion of limit mn to infinity x m minus x n equals to 0 is used to describe the definition for the Cauchy sequence. Here are the examples of the definitions, where it says that the an equals 1 over n is considered as the Cauchy sequence. In order to prove the statement, we need to let the am equals to 1 over m and an equals to 1 over n. And suppose that m is greater than n, that means that am can be minus by an, which results in 1 over m minus 1 over n equals to n minus m over mn, which is lesser than 1 over n. This also means that the am minus an is lesser than 1 over n, that is equals to epsilon. Take that the n0 is lesser than 1 over epsilons, we can get 1 over m minus 1 over n, which is lesser than epsilon for all mn is greater equals than n0. The second example will be letting the xn to be the real number sequence. And we can define the yn as the sum of the xn and zn as the sum of the xn as well. We, eh, we, we need to show that if yn converge, then that means zn is also converged. By doing so, like, we, in order to prove this statement, we need to show that the Zn is a Cauchy sequence. And in order to do so, we need to observe that for all m is in n with n is greater than m, we have the Zn equals to x1 plus until xn, and Zm equals x1 plus until xm. Hence, we can minus Zn with Zm equals to xm plus 1 plus until xn, which is lesser equals to xm plus 1 until xn, which is equals to yn minus ym by the triangle inequality. Now we let the epsilon greater than 0, and since we know that the yn converge, that means that the yn is a Cauchy, and there exists the capital N in N such that for all nm is greater equals than capital N. We have the yn minus ym is lesser than epsilon. That means that by the above observations, when nm is in N and without the loss of generality and greater than m, we have the zn minus zm lesser equals to yn minus ym, which is also less than epsilon. This all shows that the Zn is a Cauchy sequence, and that means that the Zn is also converged. Here are the theorem for the Cauchy sequence. And the theorem states that every convergent sequence is a Cauchy sequence. And in order to prove this, we need to let the an to be the convergent sequence. And in order to do that, we need to prove that the an is Cauchy sequence in limit n to infinity an equals to I. And by the definition of limit for every epsilons greater than 0, there exists m0 in n such that an minus I is lesser than epsilons over 2 for all n is greater equals than m0. If n is greater equals to 0, then that means am minus I is less than epsilons over 2, and an minus I is less than epsilons over 2. Now we can subtract am with an, which results in am minus I minus an, which is lesser equals to am minus I plus an minus I. And that means that the am minus an is lesser than epsilon over 2 plus epsilon over 2, which is equals to epsilon for all mn is greater equals than m0. Hence, this shows that the an is count as a Cauchy sequence. Here are some of the examples of the problems regarding the Cauchy sequence. The problem states that we need to show the sequence an where an equals 1 over n plus 1 plus 1 over n plus 2 plus 1 over n plus 3 plus until 1 over 2n is monotonically increasing and is bounded above by 1. So it is a convergent, and that the limit is I where 1 over 2 is lesser than I is lesser than 1. The solutions is here is down below, and it's given that the an is equals to 1 over n plus 1 plus 1 over n plus 2 plus 1 over n plus 3 plus until 1 over 2n. Then we can plug and we can add the n with 1, which results in an plus 1 equals to 1 over n plus 2 plus 1 over n plus 3 plus 1 over n plus 4 plus until 1 over 2n plus 1. With that, we can subtract the an plus 1 with an, which will get the results of 1 over 2n plus 1 plus 1 over 2n plus 2 minus 1 over n plus 1 equals 1 over 2 times 2n plus 1 times 2n times n plus 1, which is which is greater than 0 for all n in n. That means that the an plus 1 is greater than an for all n in n. This shows that the an is considered as the monotonically increasing sequence. That's all for me today. Thank you very much for listening to my presentations. I hope that I'll see you again next time. All right, thank you.